Hi, welcome to StatStuff. I'm Matt Hansen. In this lesson, we'll talk in more detail about the measurements for spread or variation, like the standard deviation or inter-quartile range. This lesson is building off the other lessons on distributions and central tendency, so it's important that you've at least gone through the lessons that are leading up to the topic of central tendency. So let's begin by quickly reviewing how spread or variation is one of the characteristics that describe a distribution.
Well, if you recall, we said that the shape of the distribution is influenced by two different characteristics. So if we have an example here of three distributions that are laid out on a scale. The first characteristic is central tendency. This is where it's referring to the location on the scale where the majority of the data points are concentrated or where they're more centralized. It's that central point where the data tends to fall, where most of those data points tend to fall like this on the scale. And for normal distributions, again, it's the mean or the average that we would tend to use for measuring that central tendency. The other characteristic is variation or spread. This is referring again to how dispersed or spread out the data is from the central tendency. So for each of these distributions, they all have varying degrees on how far spread out they are. Even though they all have the same central tendency, they are all different in how spread out they are from that central tendency. And usually for normal distributions, it'll be the standard deviation that's going to be our measurement for spread or variation.
Okay, now let's talk a little bit more about what we mean by spread or variation and why they're so important.
Well, as I just described, variation or spread is referring to the distance each of those data points are from the central tendency, again, which would be the mean or the median. So why is variation so important to us? Well, central tendency is only going to be telling us the output performance of all those data points. It doesn't, however, tell us the severity or capability of the process itself. And quite honestly, that's where we feel the most severity and the pain that we're trying to resolve in the process. That is the variation that's causing that pain. So as you might have heard the old adage, if you place 1 foot on ice and 1 foot in the fire, then on the average you should be warm. Well, obviously that doesn't reflect reality, but that's how we might normally consider the limitations of central tendency, in this case like the average. So let's explore a little bit more specifically on variation. So if we go back to those processes we've described in previous lessons between the expression of these darts, where you have process A as if it were illustrated by throwing darts scattered across the dartboard, versus process B, where they're all gathered in one spot on the dartboard. Well, if you were to look at these, which of these has the higher score? Well, process A, because there's more darts that are hitting the higher scores. And which one has a higher central tendency? Well, again, it's going to look like process A. So in that case, if we were measuring things purely off of the score as well as for the higher central tendency, then we would say process A is better. But is that really better? Which one is really better? I would argue that it's probably process B that is better because there's consistency. There's less variation in having where the darts are spread out across there. Because all you have to do, if this was a reflection of actually throwing darts at a dartboard, all you have to do is step a little bit to your left and then you'll be able to hit the target every time. However, we can't really see with process A what changes we need to make because they're scattered all over the dartboard. Well, when we reflect that in variation itself, variation is where we have less control and where we're feeling most of the pain. So the degree of variation that we feel affects the degree of difficulty of trying to correct or fix that variation, again, that pain point that we're feeling. As well, the degree of predictability affects the degree of control and comfort that we might be feeling. Well, if you recall, we had an example before of the thermostat calibration. If you had a thermostat in your house where you're trying to control the temperature, you might see that there's two ways you can have it. One that has no variation, where your thermostat is consistently 3 degrees too low from what you've set it to. Well, that's a whole lot easier to control if you were to make some sort of fix compared to setting your thermostat in. Sometimes it's too high, sometimes it's too low, and there's a lot of variation. There's a lot of pain in that variation that you're feeling, but when you have a consistency, again, where you have little variation in the performance, yeah, it may not be perfect, it might be 3 degrees off, but at least you have a lot more control and you can get to the desired output to alleviate the pain that you're feeling from it. Well, in order to understand our data, we have to first understand the central tendency as well as the variation. We need to make sure we don't just limit our research and our analysis on central tendency like many organizations do. We have to make sure we also account for variation.
Okay, now let's talk about the various ways that we measure spread or variation.
Well, there are several ways that we can be measuring the variation or spread that we use for normal distributions. The first one would include like the range, and it reflects the entire extent of the data set. from the beginning, the minimum, all the way to the maximum, the greatest point. So if we had this simple scale here of all of our data points that were plotted, this one at the lowest range would be the minimum, the one at the high end would be maximum, and the distance between all these would represent the total range, again from the minimum subtracted from the maximum. And next would be deviation. This reflects the distance a data point is from the mean, or it would be x minus mu, which is the mean value that's represented. So when we have this, again, back to our illustration, we have a few data points here. The mean, we would say in this case, would be 5, since that's the central tendency that's measured here, and if you were to add these values, you come back to 5 as your mean. Well, if we reflected x as any data point, in this case we might say 9 is one of our other data points. Well, then deviation would be 9 minus, again, the mean, which is 5, so that would give us a deviation of 4. So again, that would tell us the actual distance a single data point is from the mean. Now another one would be variance. This reflects the average square deviation, or the differences, around the mean. And the measurement for this is x minus mu squared divided by n representing the total number of data points. And you could also say it's the standard deviation squared. We haven't got the standard deviation just yet, but that's another way you can illustrate it. In this case, the variance is intended to measure how spread out the total distribution is from the mean itself. The one that's most commonly used, though, is standard deviation, represented again by this sigma value. This represents the square root of the variance. So we're taking, again, that variance, we're taking the square root of that value. Again, that's why we said the variance was really just the squared value of the standard deviation. Well, standard deviation is measuring the average distance to the mean for all of the data points. That is, on the average, how far spread out is each data point from the mean point. And it's the most common measurement that we're going to be using for normal distributions, and that's where the mean is generally used, and that's where we use the average again for a normal distribution. In the same way, since standard deviation is using average, then standard deviation would be the best measure for variation that we tend to use when we have a normal distribution. So then how are we going to be measuring variation when we have a non-normal distribution? Remember, non-normal distributions we talked about in the previous lesson about non-normal distributions is that we don't use the mean because it's not the best measurement for central tendency. Instead, we tend to use more often something like the median, which is the 50th percentile. And the reason, again, was because the 50th percentile does not move. It's always going to be a fixed point wherever that 50th percentile is. It doesn't shift like the average can shift if you have some outliers in one direction or another. That's typically going to be involved in a non-normal distribution. So in this case, when you have that and you want to measure some variation for a non-normal distribution, you can use something like the stability factor. It represents the relative spread of the data points around the median, again, that 50th percentile point. And that's going to be Q1 divided by Q3. And each Q represents the quartile. So it's the first quartile, which is the 25th percentile, divided by the third quartile, which is the 75th percentile. The idea behind using that is that the closer your stability factor is to 1, the more likely there is little variation in the distribution. So again, if you're taking your 25th percentile, dividing it by the 75th percentile, when you see that it's closer to 1, chances are that means it's much closer to or less distributed from the median. But the further away it is from 1, the closer it is to 0, then that means it's much further spread out from the median or that 50th percentile. So that's what we're looking for, the stability factor. You could also use the inter-quartile range, which is measured as Q3 minus Q1. Again, it's a 75th percentile minus the 25th percentile. That could also be used, and in that way it's used to suggest the amount of variation by expressing the range of the middle 50% of the data points. So just by simply getting that calculation of the 25th from the 75th percentiles, you're just measuring what that total distance is, that range across the middle 50% of the data points. It's a little bit different. I would tend to use more likely, though, the variation to get more of a description of the shape, at least from a variation standpoint, of a non-normal distribution when you have that kind of situation. But more often you almost prefer, if you can, to use a normal distribution. Find out why your distribution might be non-normal, and if you can find out what it is, if there happens to be any bias in how you collected your data, or maybe just within the data itself, then try to identify that and remove it if possible, or somehow work with that, or somehow normalize it if you can to get to a normal distribution. That way you might be able to use these other kind of parametrics, which are using the central tendency and standard deviation when you're dealing with normal distributions.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
Well, what are some metrics that you might have in your organization that are used for measuring spread or variation? Unfortunately, there aren't going to be many organizations that actually use spread or variation as a critical metric. So if you can't find any, then that might be actually more typical of what you see in a lot of organizations out there. So if your organization does not have any metrics like this for measuring spread or variation, then I would challenge you to try a couple things. First, identify at least 3 metrics that you use in your organization, and only look for the metrics that are at least based off of continuous type of values. Again, continuous values which tend to be numerical in nature, that is, measuring dollars or measuring something from a numerical standpoint or over time or something like that. So identify those, at least 3 of those metrics, and then for those metrics, try pulling some historical data for each one and run a normality test on that data. Now, if you run the normality test and you find that the distribution is normal, then try to calculate the variance and the standard deviation for that data set, for that distribution. And if you find the distribution is non-normal, then try instead calculating the IQR, or the stability factor, for that non-normal distribution. Now, looking at that, what do you think the results are, what they're telling you about the variation that you've seen in each of these metrics? Now, which metric has the most variation when you're comparing all 3 of those? And have you observed if your organization is more frequently overreacting to any particular change in one of those metrics? If you find that they are overreacting, then it could indicate that there's a pain point that's occurring in your organization that needs to be addressed. That is, they might be overreacting because they're not accounting for the variation. If there's high variation, that is, you might see some metric going extremely high and extremely low, and you find yourself getting into a fire drill mode where you're trying to resolve why we went so high and why we went so low, when you actually could just have normal variation occurring in your metric. Well, if you can at least measure the variation and understand how much variation you have in your metric, then you might prevent some of those types of unnecessary fire drills. You might have a better understanding when it is necessary to have a fire drill, that is, when you go well beyond the normal level of variation you expect to have in your metric.
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.